This lesson is on polynomial functions. This is section 2.2 from your book. So last time when we were talking about power and radical functions, we briefly talked about a polynomial function. And a polynomial function we've said is a times some x to the n. And we can put a little sub n by that a to say that this coefficient specifically related to that n is going to be our leading coefficient. So a sub n is our leading coefficient. So if we have 5x cubed plus 4x squared plus 3x plus 2, for example, then this 5 is our leading coefficient. And the reason it's our leading coefficient is because it's attached to the x that has the highest n. And our n we call the degree of the polynomial. So this polynomial would be of a third degree, a degree 3, because the highest n that we have is 3. So a function like this we can call, above we have f of x equals a sub n, x to the n plus a sub n minus 1 to the x n minus 1, and so on until you get to ax squared plus ax plus a naught, or a 0. So the function above is called a polynomial function, with all these x cubes and x squareds, or even a just to the 0. And a polynomial function we describe as being of degree n. So we describe the polynomial based on whatever that highest n was. So for that above example, it was 3, degree 3. Polynomial functions, in order to be polynomial, it must be continuous. And we want to make sure that in addition to having no breaks, holes, or gaps, that they also don't have any sharp corners. So if you ever see, we know one very famous example of a function that has a sharp corner, we have absolute value. So this is not a polynomial because of that sharp corner. Some polynomials you already might know include constant functions. So this is a degree 0. This is when we just have y equals 4, for example. We have a horizontal line. Linear functions are degree 1. So you have y equals mx plus b, where that x is just raised to the power of 1. That's the highest degree we have. It's degree 1. And we get a line in that situation. Quadratic functions, ax squared plus bx plus c, or even if you just had x squared or 3x squared, our highest n is 2, and these look like parabolas. So for degree 3, we call these cubic functions. So this is if you ever have an x cubed. And for degree 4, we call these quartic functions. So again, this is when your highest n is a degree 4, for example. So polynomial functions of degree n greater than or equal to 1, these have at most, so not every single time, but at most, they're going to have n distinct or real zeros. So we're not talking about the zeros that, we get an I. So if you have square root of x minus 1. We're not worried about the positive and negative. We're talking about just the real zeros, so just the real numbers that we get out of this. In addition to having n distinct zeros, these are going to have n minus 1 turning points, or extrema, where the function changes from increasing to decreasing, or vice versa. So if we look above at this degree 1, for example, mx plus b, we had a line. We're going to expect to probably intersect this x-axis somewhere. So we're going to have a distinct 0, maybe over here somewhere to the left of that line. And we don't have any turning points. We don't have any maxima or minima, no extrema, because n minus 1 is 0. So we have 0 turning points. We have 0 places where we go from increasing to decreasing, or vice versa. For degree 2, so this is an x squared function, you might have 2 zeros. So you could have x squared minus 3. You're going to cross that x-axis at multiple locations, which means you're going to get 2 zeros. And also, n minus 1 turning points for x squared, so 2 minus 1, we're going to have 1 turning point. We're going to have one place where we have either a max or a min. And this goes on and on. So for x cubed, you might have 2 turning points, or some 3x cubed plus 5x plus 4 or something like that, you might have a situation like this, where you cross the x-axis at 3 points, that's the highest you can cross, and you have 2 turning points. So you have 2 extrema. In this example, I drew a minimum and a maximum. So the behavior for graphs, as we know for different degrees and coefficients, we know that we care about whether or not a sub n is greater than 0 or less than 0, so we're worried about it being positive or negative, and also the degree n. So if we have x squared, it does something. If we have x cubed, it does something else. And we're talking about the right end and the left end behavior. So just as a reminder, for n is even, we're going to do the same on the left as whatever we were doing on the right. For n is odd, we're going to do the opposite on the left as whatever we were doing on the right. And what are we doing on the right? That's dictated by a. So when a is positive, when a is greater than 0, our right end behavior goes up. When a is less than 0, when a is negative, our right end behavior goes down. So if you can just remember the graphs, negative x squared, or positive x squared, and negative x cubed, and positive x cubed, you're going to remember all 4 of these rules and what happens to our end behavior. So there's another test that we can apply. This test is called our leading term test. That's what we've been doing when we're trying to decide what's happening on our end behavior. And this determines our polynomial end behavior. So when you look at your a and your n, this is called the leading term test, and it helps us determine end behavior. And I think that it's helpful to remember x squared and x cubed, because those are graphs that maybe you're more familiar with, and they'll help you make guesses about what's going to happen for x to the 5th or x to the 20th, for example. So multiplicity of zeros is also something that gives us information about what our graph is going to look like. This tells us about the inside of our graph, where we're crossing the x and where we have zeros. So in order to find the multiplicity of zeros, there's 3 steps. Step 1, we want to rewrite the polynomial in factored form. So this means we want it to be in our most factored form, so you might get 2x times x minus 1 times x plus 3. That would be a factored form of writing whatever polynomial we started with. Step 2 is to find the zeros. Step 3 is then to analyze the power of the factored term, of the factored form. So in the above example where I had 2x times parentheses x minus 1 times parentheses x plus 3, let's put a 4 at that x plus 3. So we're raising x plus 3 to the power 4. So we might have a multiplicity of 4 zeros. But the first thing you need to do is to find that leading term to make a guess about what's going to happen. And that leading term is going to include all of these x's, including that x to the 4th that we have. So multiplicity of zeros, in order to understand how those behave, when you have an odd multiplicity, that means at the x producing that 0, f of x is going to cross the x-axis. So at whatever x made that 0, you're going to cross the x-axis. For an even multiplicity, at the x producing that 0, your f of x is going to touch, just barely touch the x-axis, and then it's going to turn around. So for crossing the x-axis, we know what that looks like. You might just have a cross like this, right? That you might have a 0 right there with a multiplicity of 1, for example. And then if we had a multiplicity of 2, maybe we would just hit at that point and bounce back off. So let's do an example together. Apply the leading term test, determine the zeros, and state the multiplicity of any repeated zeros. So we are given the example f of x equals negative 2x times x minus 4 times 3x minus 1 cubed. So we want to first multiply to find the leading coefficient. So we don't know what our leading coefficient is yet, right? We don't know if it's cubed or, I mean, we can make some guesses. We have an x out here that we're going to multiply with an x out here that we're going to multiply, and then this 3x cubed that we're multiplying. And so that's how we're going to find that leading term. That's going to give us information about the end behavior of our graph. So first I took 3x minus 1 cubed, and I knew that that 1 isn't going to affect that leading term. It's not going to be the biggest x that we have, so I just said 3x cubed, and we get 27x cubed. And I know that that 27x is then going to multiply our first term and our second term. So then we have x by itself, that's just this x minus 4 is just raised to the power 1. This negative 2x is just raised to the power 1. And so we have negative 2x times 27x cubed. This gives us a negative 54 x to the 5, x to the 5th. So our a to the n, our leading coefficient, becomes negative 54. What do we care about for a? We care about whether a is positive or negative. So far we already know that we have a negative a, which means as our graph goes to the right end behavior, it's going to fall. We know it's going to be decreasing. And we know that n equals 5. What does it mean when n equals 5? Well, that means we have an odd n, which means that our left end is going to do the opposite of our right. So already, just by finding out your leading coefficient, you know your graph is going to do something like this. It's going to start up on the top left. As we go to the left end, we're going to go to positive infinity. As we go to the right end, we're going to go to negative infinity. The next step we need to do is to find the zeros and their multiplicity. So if we look at this factored form, we have negative 2x times x minus 4 times 3x minus 1 cubed. That's back to the original factored form that we were given. We were already given this equation in the factored form. And so each of these things, because we have multiplication, is going to produce a 0. So the 0 at negative 2x, what is going to make that term negative 2x 0? Well, that's just going to happen when x equals 0. And the multiplicity for that is just 1, because we don't have this negative 2 times x raised to anything. We don't have it raised to the 3rd or the 4th or the 5th. So we just have a multiplicity 1 right here. For x minus 4, when does x minus 4 equal 0? Well, x minus 4 equals 0 at x equals positive 4, right? If you plugged in 4 minus 4, you get 0. This again is multiplicity 1. For the last term, we have 3x minus 1 cubed. And so that cubed is going to affect our multiplicity. It's not going to affect where our 0 is. Where our 0 is, we just say 3x minus 1. Where does that equal 0? Add 1 to both sides. 3x equals 1. We're going to divide by 3. We get x equals 1/3, a positive 1/3. And that has a multiplicity of 3. And so what do we care about for these multiplicities again? If the multiplicity is odd, it means at the x producing the 0, f of x is going to cross the x-axis. So that means all of these multiplicities are odd. We're going to have a bunch of places where we cross, but we want our graph to look like it looks in the above picture, where we were increasing as we were going to our left end. Our left end was going to positive infinity. Our right end was going to negative infinity. So what does that look like? If we were to make a guess, all right, well, at x equals 0, we have something going on. At x equals 1/3, we have something going on. And then over at x equals 4, we have something going on. We know that we're going to cross at x equals 0. We're going to start up at the top, and we're going to cross. Then we're also going to cross again at 1/3. And then we're going to cross the last time at x equals 4. This is what I would expect our graph to look like for all of these locations. And if you look below, this is what it looks like. So maybe my loop was a little bit big from 0 to 1/3, but we kind of got the right graph. That's it.